Okay, hello everyone. So today we discuss the Blob model, which we started seeing during the lecture, which is a model of stretching of a polymer, but it can be applied to several situations. So we start from the energy of springs, connected springs making a polymer, which is described, these are described by the following Hamiltonian. Ri minus Ri minus 1 squared. And these are stretched by a stretching force F. As usual, this is applied to the end points. Okay. So our model is like this. The force is applied to the last monomer. Monomers are connected by springs. And so on. So continue the last monomer. Force F and force F here. Okay? All right. So, first of all, at F equal to 0, we can calculate what is the average stretching of this system. Okay. So we call A squared. We define it as the extension of the springs, so it's m plus 1 minus n squared at force equal to 0. Okay. Then I don't do the calculation, but if you do the calculation, you can find that the distance between, say, if you start from monomer n, and you calculate the distance, the positions of monomer n and monomer n plus m squared, this can be shown to be equal to m a squared plus m squared a squared divided by 9 f times a divided by kbt squared. Okay. So here we see that this quantity, well, there are two terms in this quantity. There is this m a squared, 1, and there is another term, m squared, a squared, which multiplies the force, and this is the 2, okay? So if we plot these two, okay, so, this quantity is the distance squared between two monomers, one monomer here and one monomer further away. So it gives the average, somehow, square distance between these two monomers, okay, and we recognize two contributions, and if we plot the two contributions separately, in horizontal axis we put the monomer number, m, the separation, so m, so of course this quantity is translational invariant, so it does not depend on the index n, it only depends on the index m. So if we calculate this, and so if we plot the two, we have the first contribution is a straight line, okay, and the second contribution is a parabola. Okay. So we use the same colors, okay, the first one is the red color, the 1, the other one is the blue color, line 2, okay, which we plot here. I hope it's visible on the video. All right. Okay, so these two define a characteristic monomer number. So when I look at the intersection of the two, I deduce a characteristic value of monomer number, which I call a G. It's where the two balance, they have more or less the same, they have the same value, okay? It doesn't mean that if I go to monomer distance much smaller than G, this is dominated by the first term, the 1, for m much larger than G, this is dominated by 2, okay? But what is 1? This is the rule, this is the scaling law that we have for free polymers, okay? Free polymers, the average square distance between two monomers, we know it's scaling as m, the a squared, you remember that for a free ideal polymer, the end-to-end distance square scales as n a squared, which is exactly the first term, okay? And this first term refers to two internal polymers, okay? So this is two internal monomer of the system, all right? Now, when these two balance, and the second one is due to stretching, okay? And it's a different shape, it goes as m squared. So when the two balance, we have a characteristic number of monomer, and this defines what we call a blob. Okay, so I can erase this one. You recognize that this one is specify the first terms. So the number of monomer in the blob. What is the concept of the blob? So G is what they call number of monomers in a blob. Okay, so which means if I start from monomer N, so I have my polymer here, if I start from monomer N and I look at the distribution of the neighboring monomer, I go to monomer N plus 1, N plus 2, N plus 3, okay, it will be a random walk like that, as we know. Okay, so if I stay within, say, start from monomer N, if I stay within a range such that I look at the next M, but this range is much, much smaller than M plus G, okay, and then I notice that you can't see this, so let me redo this, this drawing. Okay, let me try again. Okay, I start from monomer N, okay? I start from monomer N, I have small spring, I have here the monomer N plus 1, I have here the positions of monomer N plus 2, and so on and so on. And I move around, this is a random walk, okay? Okay, and I continue, right? Okay, if I stay within the range G, so I stay within N plus G, actually this distribution of polymer is dominated by the first law, by the law number 1. This is that same distribution as an ideal polymer. It's only if I go beyond this range that I see that is dominated actually by another law. And so in other words, I see the effect of the force is only at the distance N plus G, beyond this N plus G moment. Okay, so the picture, if I draw it now for the third time, okay, the picture is like this. I start from my monomer N, I have a distribution of monomer, but up to a certain distance I see the effective of the stretching, that actually the polymer is more stretched, is not like an ideal random walk, is stretched in the direction of the force. Okay, and this happens if I start here at the monomer N, number N. This happens at the monomer N plus G. Beyond the N plus G, I see that actually the structure of my polymer is a stretched one. Okay, so if I try again to draw N here, so the structure of the polymer actually separates into blob. I start from the first monomer, the monomer 0. I have monomer surrounded by monomer, but if I reach the monomer G, okay, then I'm entering into another blob, and I reach the monomer 2G, I am in another blob, and I go into another blob, so I can draw some blobs like this, and actually you should not be misleaded. There is not actually really a boundary between separate blobs. The concept of blob is more like a typical number of monomers that are inside one region that is basically governed by ideal polymer law. Okay, right? So this is the structure of my polymer. So is the polymer, I see that this polymer is actually stretched. It tends to be elongated in the direction of the force, but I see that only if I go beyond a certain characteristic scale of number of monomers, and this scale is G, okay? Therefore, I can also define here the blob size, psi of B, which in ideal polymer, it's given by how many monomers I have. So characteristic distance between two monomers times the scale, the number of monomer to the power 1/2, the number of monomer on the blob. So this is the typical distance psi B, the size of a blob.